Greetings, everyone. A very warm welcome to you all to the webinar hosted by the North Central Climate Adaptation Science Center, which is based at the University of Colorado, Boulder. I'm Imtiaz Rangwala, the climate science lead at the center, co-hosting this webinar with my colleague, Heather Yoakum, who is the social science lead at the center. We bring you these webinars to facilitate a discussion of science, research, and best practices related to adaptation and resource management under a rapidly changing climate, with a focus on the north central US that encompasses the Missouri and the upper Colorado River basins. Before I introduce our speakers, a quick word on housekeeping. We are recording this webinar, and you can find all our webinar recordings on our website. During the webinar, all participants will be muted, but you will have the ability to unmute during the Q&A period at the end. We, however, encourage you to put your questions and comments in the chat anytime during the webinar, and we will start with those questions first during the Q&A in the order they are received. We'll end the formal part of this webinar at 10 a.m. Mountain Time and stop the recording at that point. After that, anyone who wishes to stay on to engage in a more informal conversation with our speakers is encouraged to do so. And now I'm very excited to introduce our speakers for today, with whom I have had a very enriching long-term collaboration. I'll start with Catherine Hegewisch, who is a project scientist at the University of California, Merced, where she's an applied researcher in the Applied Climate Science Lab. She maintains large climate data sets and develops web tools to improve the accessibility of climate data. These data and tools have been used in national climate assessments and in peer-reviewed scientific publications, and are used every day by decision makers to monitor the climate. She's the lead developer of the Climate Toolbox, which we'll cover quite a bit in today's presentation, which is an online suite of over 20 web tools that provide climate and hydrology summaries on maps and graphs to inform decision-making related to heat stress, drought, agriculture, and wildfire danger. Catherine has a PhD in physics from Washington State University. Next, we have John Gannat, who is a spatial ecologist with the U.S. Fish and Wildlife Service in its Ecological Services Program, based out of the Legacy Region 6 office in Lakewood, Colorado. John assists Fish and Wildlife offices across regions 5 and 7 with analytical, geospatial, and statistical needs for listing or delisting species under the Endangered Species Act, species status assessment. John's work also support habitat conservation plans, recovery, critical habitat, climate vulnerability, and mitigation. John has a PhD in tropical environmental studies and geography from James Cook University in Australia. And the final speaker is yours truly. The title for today's webinar is climatetoolbox.org, a discussion of climate applications to support quantitative climate change impact assessment and scenario planning. So I'll kick off the presentation, and Catherine, if you can go to the next slide, please. So much of our presentation today will be focused on the Climate Toolbox, the introduction to the toolbox, the underlying data, and more specifically, discussion of two tools that we have developed out of this ongoing project or improved to support quantitative scenario planning application, and there'll be live demos around those tools. Next slide, please. So first, I'm going to get into some background and context related to climate uncertainty and how we're trying to incorporate that especially in like in the Fish and Wildlife Service species status assessments, but other projects that we are doing with our stakeholders. Next slide, please. So there is a general agreement that climate change is rapidly altering environmental processes, reshaping and transforming ecosystems at times in surprising ways. And you can see that in large-scale mortality events, invasive species issues, and impacts related to extreme events through wildfire and flooding. And these are expected to intensify in coming decades. And so land managers are strongly encouraged to better anticipate these impacts and develop science-informed adaptation strategies. Next slide, please. But one of the wicked problem is the issue of uncertainty. And there are various forms of uncertainty, and today we'll mostly focus on climate uncertainty. And that arises from the uncertainty around the magnitude and direction of future change. So for example, how much water it would be in future. Will there be more or less water? How will the severity of different extreme weather and climate events change? These are non-trivial questions to quantify sometimes. And then there's the issue of what emission scenarios will play out, and how climate would look at different future time horizons, and how to incorporate these pieces into the decision-making process. Next slide, please. Oh, and of course, we encourage folks to integrate those uncertainty in their assessments. And one approach is to use scenario-based methods, which we have seen an increased use by stakeholders and practitioners in recent times to do climate change impact assessments. And these essentially, the method essentially is not to emphasize one deterministic future, but work with multiple plausible futures that are divergent, and generally not assign likelihoods to those futures, and explore strategies that are robust across those futures. We are finding that scenario planning is a functional and effective approach to consider when uncertainties are pretty high. Next slide, please. And so one place where we have been bringing in scenario-based approaches is an application to the Fish and Wildlife Services species status assessments. And since 2017, we have been working on different projects involving different biologists on those projects, and developing quantitative information for use on those projects. And you can see a list of different projects here. Next slide, please. And so very briefly, the process involves mapping out the uncertainty space in climate, selecting a few climate scenarios, and then quantifying those future across those scenarios. And in the example here, you can see that uncertainty space is shown through this bivariate plot, and which is one common way that's been applied across different methods I've seen out there. So, but there could be many other ways you can imagine where you can explore the uncertainty space and select these scenarios. This is one of the simpler ways where you plot changes in temperature and precipitation, but you can bring in multiple different variables across these axes, as Catherine will show later on. Next slide, please. So once you have selected these scenarios, you can quantify climate change across the scenarios. And one of the ways we have done that is developing these SSA climate metric tables, or climate summaries, I've been commonly calling them, quantitative climate summaries, where you can quantify change across these different scenarios, and take that quantitative information to do all kinds of brainstorming sessions where you brainstorm impacts and strategies. But these are not the only quantitative information you can generate, and Catherine will show later on that you can get spatial layers, etc., based on these scenarios. So at one time, we were getting a lot of requests around developing these kind of information for different SSAs, and the motivation was to automate the process and make the process more efficient. And that's was kind of really the context around which we developed the collaboration with Catherine, and which has resulted in development of new tools and improvement of other tools. And now I'll hand over to John to go through, to share some thoughts around how climate applications have been done in the SSAs.
Thanks, Imtiaz. Can you go to the next slide, Catherine, please? Yeah, I just wanted to say a few words about how fortunate the service has been to have the collaboration with Imtiaz and Catherine for trying to get our heads around the climate issues affecting our species, and particularly the Climate Toolbox has been super helpful for us. And the species status assessment, I don't know if, for those of you who don't know, is kind of the main foundational science document that the service generates to try to make the most informed listing decision when we have to decide whether or not something should be listed as threatened or endangered. And the trickiest part really for our biologists is, the species status assessment is kind of a document that kind of gives an overview of the current and future condition of the species, or what we think the future condition is going to be in the future. But that's the trickiest part, is the future condition, because in most cases it usually has a large climate component, and there's a lot of uncertainty, not only in the climate scenarios, but also in the species responses. And it can be, our biologists most of them aren't climate experts. So we really lean heavily on Imtiaz and his interpretation of the climate information and Catherine's tools to basically help us get our head around what potentially could be future issues for a species that we're working on for a listing decision. And can you go to the next slide, please? So I guess through we've been working together for several years, and it's kind of been an iterative approach for tool development. And we've had really great luck with Imtiaz and Catherine, providing feedback from the service side on kind of things that are really problematic for us. And in the climate metric table, I think Imtiaz mentioned that earlier, but a lot of time was spent by myself and Imtiaz and our biologists trying to generate these climate metric tables through Excel spreadsheets and such. And Catherine automated that process, which has been a huge time saver for us. Another big development that she added was a GIS shapefile upload, where we can actually upload different species population units spatially, and then generate those tables based on those polygons. And again, another huge time saver, and it also improves accuracy for each of those population units in terms of the climate metrics that we get on that backside. And then finally, just the visualization tools. And I think Catherine's going to go over the climate scatter tool, but that's probably one of the most used tools on the service side, because it helps us kind of bookend, the possible future scenarios for any given species. And while those tools really help us, I think in terms of saving time, we still do lean on the CASC to help us interpret what those outputs actually mean for the species. And then we have the added kind of challenge to give our best guess about what those potential futures could mean for in terms of the species response. So those are all really challenging. There's a lot of uncertainty around all of that, but I think the toolbox and the support from the CASC has really helped us, given that we don't have a whole lot of bench strength on the climate side within ES. That's not a blanket statement, but in general, a lot of our staff don't have a lot of a strong climate background. So I'll leave it there.
Okay, and so I'll go on talking about the Climate Toolbox. Thanks, John and Imtiaz. So the Climate Toolbox is a collection of over 20 different tools which can be used to explore summaries of climate and sometimes hydrology, past, present, and future. Here is the landing page for the Climate Toolbox, which you can get to by opening any web browser and going to climatetoolbox.org. It is free for use, and you can get to the tools once you're on this landing page here by clicking on the Launch Tool button under any of these different tools. So you can see here that these represent the different tools. And the goal of the Climate Toolbox is to help to make climate data accessible for decision-making related to climate, water, fire danger, and agriculture. And these data sets are scientifically sound. They've been used by climate researchers and published and peer-reviewed literature like the Climate National Assessments. And the toolbox takes the data sets and makes them usable by anybody that's interested in learning how to use them. And when you do open a tool, the tool opens in a browser, and this is kind of the view that you see here. So before getting to the actual tools, I wanted to describe the power of the tools. And the power of the tools really comes from the data sets that they're built based on. And in the toolbox, we have three different time scales for tools. We have past or real-time data, we have forecast, and we have future projections. And the past data is coming from GridMet. It doesn't say that here, but GridMet is a blend of ground station and satellite daily data from PRISM and from NLDAS2. It's from 1979 up until yesterday, and it's gridded data over the contiguous USA here. And we have forecasts from CFS version 2 and the North American Multimodal Ensemble Project. Both of these have been bias corrected to GridMet. So the statistics are consistent. And then we have future projections from the CMIP-5 project. And soon we'll also be having projections from the CMIP-6 project, as these are being run right now. But these are projections, daily projections, out to 2100. We have 20 different climate models, and we have 2 future scenarios, the RCP 4.5 and 8.5. And this also has been part of the downscaling process. These are downscale data here. And they have also been bias corrected to GridMet, the same GridMet. So we really have a consistent set of climate data here, past, present, future, all with the consistent statistics to GridMet. And so this future, I want to talk a little bit more about the future data, as it's really important to our scenario planning for this work for this project with NTS and John. So this data, the future data originates with global climate modeling, where scientists are using computer simulations to conduct experiments and test hypotheses about our changing climate. These are done by simulating global weather in the atmosphere, ocean, land surface, and cryosphere by chopping up everything into 3-dimensional grids. For example, a 3-dimensional grid cell here of a section of the atmosphere might look like this, where inside there is an assumption of what's going on with the clouds, if there's precipitation or not, or what form that precipitation takes. And the model connects all of these aspects of the Earth system and has models for feedback mechanisms. There's a lot of science that science knows here, but there are some big things that scientists are still working on as well. So back in 2010, which I realized was a really long time ago, the Intergovernmental Panel on Climate Change, or the IPCC, created a project called CMIP-5. So it was the 5th phase of the CMIP project, to create an ensemble of future climate projections. So the global climate models were run by modeling centers all over the world from many different countries. In total, I think there were over 40 different models, probably from 20 different climate modeling centers. And for the toolbox, we used 20 of them that supplied daily data of temperature, precipitation, humidity, wind, and radiation. So we were specific about meeting those different variables, as those are the ones that are useful for ecological and agricultural modeling, and even fire danger modeling as well. And each model ran the same climate experiment or a simulation of global weather for a historical and a future time period. For the historical time period, simulations started at some pre-industrial initial conditions of greenhouse gases, and we extracted 1950 to 2005. And then for the future simulations, there were 4 key emission scenarios labeled RCPs, or representative concentration pathways. And where here you can see the differences on the graph over time of the radiative forcing between these different ones. And in the climate toolbox, we have 2 of these. We have RCP 85, which is a high emission scenario. It was a business as usual extension of our pathways back in 2010. And now it's considered not as realistic due to the lessening of use of coal worldwide. Then we also have an RCP 45, which was a low emissions, a reduced emissions pathway when there's global mitigation of the emissions to 2100. So we'll see these RCPs and these models in our tools. And so it's important to know that this is where they're coming from. They're coming from these model experiments. And then the outputs from those global climate models, the coarse outputs are often like 200 miles on 200-mile grid cells. They vary a little bit by the different models, but that's really coarse. And you can see, like, for a state like Colorado, there might just be 20 grid cells covering the whole state. And that's a very complex a state with a lot of complex topography. And so there's 2 different kinds of downscaling, and one of them is statistical downscaling, where biases are removed from the data using a training data set. And we use the training data set of GridMet. And the downscaled product, then we increase the resolution of the data. So it goes from 200-mile grid cells to 2.5-mile grid cells. And this is the resolution of GridMet. And then it also has these biases removed where it's using the statistics of the GridMet data set. And you can see there's a much finer resolution. And again, this data is actually over the contiguous USA, even though I've only shown here the Western USA. So these data have been downscaled. And then the result is our future climate data set. It's called MACA. It's the multivariable adaptive constructed analogs method. We have 20 different models here shown here. We have 2 future scenarios, and we have daily projections from 1950 to 2099. And that data, the downscale data, we have variables like temperature, precipitation, humidity, wind, solar radiation. And that data then that was produced at our lab at UC Merced, formerly University of Idaho is where we produced it. And that data, the MACA data, has been run through different models. We ran it through a fire danger model. It was the National Fire Danger Rating System using Fuel Model G, and we generated some fire danger metrics like energy release component and burning index. But that MACA data has also been run through some different hydrology data models, such as the VIC model, the variable infiltration capacity model, was led by Dennis Lettenmeyer and Bart Neeson at the University of Washington. And also the MACA data was run through the monthly water balance model by Hostetler and Alder. And so these data are also in the climate toolbox as well as the national, the fire danger rating system. And this fire danger rating system data is used to assess, like, Smokey the Bear fire danger ratings for in your national parks and forests. And the cool thing about the climate toolbox on this data is that we don't just have these raw data of climate, of temperature and precipitation, or the water metrics that are coming from, like, the hydrology models, like snow water equivalent, soil moisture and runoff. We also have a bunch of derived metrics. One of the derived metrics might be days since having 1/10 of an inch of precipitation. Or from the temperature data, we derive what the coldest winter day is each year, or the day of the first fall freeze, or the growing seasons. We also generate potential evapotranspiration and some drought indices. Yeah, so we have a bunch of drought derived indices in the climate toolbox that help to make this data more accessible for decision makers that are often using these derived metrics and not just the raw climate variable. See. Oh, whoops. Yeah. Okay, so at this point, I'm going to go live into the Climate Toolbox. Let's see. And we're going to look at one, how to do things in the Climate Toolbox, and then we're also going to next look at the future scatter tool and the newest tool, the future climate scenarios. So this is the Climate Toolbox. You can get there by going into a web browser. I'm using Chrome, and along the top here is kind of like your information and your guidance. So like we have some different information on the data, a list of the tools here, and as well as the list tool here. We have some information videos, and some case studies and some tool summaries and some other guidance information. And then in the toolbox, we have this list of tools here. And again, there's like over 20 now. And there are a bunch so I just listed off a whole bunch of variables. And one of the most confusing things about the Climate Toolbox is that each tool, so when I open like a tool here, and I get the climate tracker tool, and I can choose location, I can choose the data. There's a whole long list of data here that I can use for this specific tool. And for each of the tools in the Climate Toolbox, it's actually different which variables they have in them, because some data is more appropriate for the different visualizations than others. And so one of the most confusing parts is that if you are interested in learning more about a specific variable, you don't necessarily know which tool to go through to. And so one of the first tools you can look at, if that is the case, is a Find Your Variable tool. And this tool basically just gives you a reverse lookup of like, these are all the different variables that are in the Climate Toolbox. So we have these raw variables, we have a whole bunch of agricultural metric type tools, we have cold hardiness zones, climate water deficit, we have some energy metric tools, some drought indices and hydrology. You can see there's like a lot of different metrics. And if I select one of these, like for example, snow water equivalent, I get a list of tools here that has snow water equivalent information in them. So you can see that there's actually only 6. So out of the 20, there's six tools that have snow water equivalent summary information in them, either for the future or the historical. Also, and then this tool can also give you some idea of where to find that information. Also, the naming of the tools gives you a little bit of a hint as to the nature of the tools. So we have the historical climate stack scatter, the historical drought recovery. These are the tool is looking at past data. We have subseasonal forecasts and seasonal forecasts. These are forecasts for the next month or the next 7 months. And we have future tools that are all like named by future crop suitability, future climate analogs. And these are dealing with the future climate data. We have a general purpose data download tool that helps you to get some of those. And we also have a general purpose mapping tool, is the historical and future climate mapper. And that's this tool here. And that basically has like all of our data sets where you can see map summaries of the different data sets. Yeah, and so I'm first gonna look at the future scatter tool. And there's a historical scatter tool, but there's also a future scatter tool. Someday those may get merged, but maybe they won't. And so this is a tool that is part of the scenario, is a first step at the scenario planning, where you can see 2 variables at once, and you see a scatter of the different projections for each of the models. And so here, we're looking at a point location, and we can actually set that location. I'm going to show that in a second. But here, this graph, like these gray dots represent the 20 different models for the historical period. So they're kind of like the benchmark for looking at projections of precipitation on the annual winter precipitation on the y-axis here, and summer maximum temperature on the x-axis. And then there's a big dot for the mean of those 20 different models. You can see the mean here. And you can also turn these things on and off by like clicking them. So in the legend, so that's another thing that kind of traverses across the whole toolbox. And then, yeah, so each of these just represents a future projection for one of the different 20 models. And here, this is the RCP 8.5 here, but you can change that as well. So we can select a location, and we can select a location. So right now I have a selection for point location, and if I look at the point location, I can either select a location by entering in a location in the geolocation setter, and it'll, a marker will appear, and then I just have to hit set location. I can also drag it. I can enter the coordinates directly, 45, and it'll update. I can also click on this button. So sometimes it's useful to know that because this is gridded data, and the gridded data is 1/24, or this is the 2.5 mile grid cells. It's useful. The data that's coming back is the data that is within a grid cell center. So basically, if I click on this, I can see the grid cell centers. And so here I have to get down to a certain zoom level. But so these are my grid cell centers, the little dots, and these are actually my grid cells. And if I select a location here, in one of these, the data that gets returned is the data that corresponds to that grid cell center. And that grid cell center is somewhat the data that is representing maybe an average over that grid cell. If I move my coordinate, if I move my marker into another spot within that same grid cell, it's going to return the same data. So that can be useful because you may be thinking that you're getting different data by being more precise and, maybe giving like 10 digits of accuracy here for the coordinates. But if you're in the same grid cell, you're going to get the same data. And that can also be important for drawing a polygon as well. Yeah. So this is the point location. We also have, you can set a rectangular area by drawing a, let's see. So we can set a rectangular area by either modifying the coordinates of a bounding box or moving a bounding box. You can also choose a state, a county, a watershed. It's interesting. In the tool that we're going to look at, we also have some other areas. Some other areas added onto this. So I'll point that out when we get into the future climate scenarios tool. So like with the counties, you can select different counties here, either from the drop down, or you can select it from the map. And then one of the newest tools that John actually referenced is that you can use a custom polygon. So here, the custom polygon, when you select a polygon, you're getting data back that is corresponding to the area average of the data within the polygon that you select. So one of the things you can do is you can draw a polygon. So I can just simply draw a polygon here. And I can also see like where this polygon like fits with the grid cells. So I can see if the resolution of my polygon really matters, if I'm going to get, more grid cells by refining it. And I can also upload a shapefile. So I can upload polygons from a shapefile here. And so I'm just going to show an example of this. Let's see if I can do this quickly. Let's see. I should have put this in a different spot, but I didn't. Okay, custom polygons. Here, this is one of the polygons that I got from John, actually. And you can see I just uploaded it, and it's on the map, and the regions are labeled, and you can also select from the regions here. These are the different shapes. These are the different columns that are in the shapefile here. And then this is the drop down of choices that go along with that. So I can use that to get an area average of the data for my future scenario tool. And I just have to set location, and then I'll be using that. And you can see that it's here underneath the location. And then for this tool, you have to make a request. Once you've filled everything out, you make a request to actually update the data. So this takes just a little bit more processing. So I'm actually gonna go back to point location. Yeah, so that's pretty good. So then for looking at like a species, for the scenario planning, I might consider like the ptarmigan, that has been used for the SSAs. And here I can create a plot for like the y-axis. I can put mean temperature, and I can select one of the seasons. So I might just select the annual mean temperature to look at the different projections and see how they vary, and see to select a scenario. So I'm going to select January through December, but I can also choose winter, spring, summer, fall. And then I'll look at precipitation, and I'll also look at annual precipitation here, and this is going to be on the x-axis. Yeah, if I go under analysis, I can change like what I view here. So here I'm looking at a fixed scenario of RCP 85 and a fixed time period of the mid-century 2040 to 2069. That's this one. I can also fix a time period, maybe like mid-century, and view both RCPs. So that's what I'm going to do. I'll do that as a first request. And you can see it comes back pretty fast, and I get a whole bunch of stuff back. I'm going to turn off the means just to make the graph a little bit better. And you can see here then that the gray dots are the scatter for the historical, and the yellow are for RCP 45 and for 85. And these are showing the actual values. So you can see here, you have a mean of 50 degrees for one of the scenarios. This is basically the space of projections from the different 20 models for the RCP 45 and 85, and then also for the historical. If I want to, sometimes it's a lot better to look at changes instead of looking at where the historical is and guessing where these future projections are with respect to the historical. So you can click the show changes button and re-request. And here I'm looking at changes with respect to the historical means. And so this dashed line right here is basically represents the mean from the historical data. And then for the mid-century, now I'm looking at changes in annual temperature on that y-axis, and changes in annual precipitation on that y and the x-axis. And for scenario planning, like AMT has showed this graph previously, I'll also change to a spot more appropriate for the ptarmigan, maybe outside of Denver. So I've got 3.39 and 105.90. I'll go with that. And see, so that moved it to a little bit outside of Denver here. Yeah, and which is a spot that's more of an appropriate habitat for the ptarmigan, I think. And then I'm going to make a request again to update the map for that. Yes. Okay. And so one of the first steps in scenario planning is then to look at these projections, the different model projections in the two metrics that you think are most interesting for your species, and where we've chosen annual temperature and annual precipitation, and to look at the spread of or the space of projections from the different models, where we have here both RCP 45 and RCP 85. So we have 40 total dots on the screen here, 20 models for each of those two scenarios. And basically we look at this, and in the temperature space, which is the y-axis here, these are the hotter models, the ones that are at the top, and the ones at our bottom are the cooler or the less hot or warm models. And then in the precipitation space, the ones on the right here are the ones where the changes in precipitation were increases. So these are the wetter models. And the ones on the left side here are the drier models, that they were decreases in precipitation over the historical. So we look at the space here, and a lot of times what we do is we look for maybe for our species, we're concerned about how our species is going to fare under a hotter, wetter climate. And so we look for a hotter, wetter model from our space. And so like a hotter, wetter model would be up at the top, and it would be on the right side. So it would be like one of these guys here. So we can choose maybe the Meroke ESM Chem. There's another tool here, and yeah. And then we can also look at like a hotter dryer model, which would be hotter again at the top and to the left. So this one might be a good one here, the IPSL model. And then sometimes we look for a model that's close to the model mean. And so that might be a model that's pretty close to that giant dot for the RCPs. And then these would be like cooler models too. So it all depends on your different species. In this tool to help John like get data from these scatter plots, we have a scenario table down here at the bottom, which you can turn on with this click of the button. And what it does is that then when you click on the dots in the tape in the graph, so for example, I choose this one to be my hotter, wetter model. If I click on it, the data actually goes into this table. It just helps you to like with record keeping a little bit. And here I've got a hotter, drier model. And if I click on that, it'll add it to the table as well. I can click on a model that is cooler, maybe more moderate.
Catherine, I just want to do a quick time check. We have about 5 more minutes.
Oh, 5 more minutes. Okay. All right. So anyway, so then these are the models that we choose from the scenario planning. They represent models that are like hotter, wetter, hotter, drier. And then for the scenario planning, we created a new tool for this project. It is the future climate scenarios tool. And future climate scenarios tool. It is here. And what this tool does is it creates a report summary. So it creates those climate metric tables that MTS was talking about. And again, you can select the location. Interesting. I know that we also have we have Indian reservations and US forest areas that I thought I added here, but it's not quite here. But you can select the future time period. So once we've gotten those scenarios from the scatter plot, we've got these IPSL, the Meroke ESM Chem and the IPSL. We can use that in this tool to get actual projections of some different derived metrics that might be of interest for the species. So I was selecting the 2040, the mid-century, and I've got a hot wet model. The one that I chose here was actually RCP85 from Meroke Chem, so I can choose 8.5 and Meroke Chem as one of my scenarios. I also had the other one was the IPSLR, and that was also 8.5 and IPSLR. I think that's what we had. Yeah, MR actually. So this is how kind of like you would fill out. So I'm going to look at 2 scenarios, and then for some different metrics, there's annual metrics, so you can look at coldest winter day. That might be an interesting one to look at. Hottest summer day, day of first fall freeze. Maybe some of these growing degree days might be useful for the forage for your for the ptarmigan, and then also some things that might affect it as far as pure climate. So seasonal might be summer max temperature for stress. Winter precipitation, maybe correlated again to the growth of food for the ptarmigan, and maybe snow water equivalent might help for protection. And so when you basically filled out these different metrics that you want and the scenarios, then you can go down and hit view report, and it makes that climate metric table that MTS was referring to. So here we've got all this data is for the hot wet model, the hot model, and it also gives the historical value. And each of these metrics that we chose is one of the rows in the table. It also has the location that we selected here, which I didn't set to be the ptarmigans, but I could reset that. So that's what it produces as the table. You can also go to download spatial layers, and all of the different metrics that were selected, you can click on and get download either a NetCDF or a GeoTIFF and upload the actual map into ArcGIS or QGIS and do your own mapping for over your specific area. Yeah. And I believe that is all for the future climate scenarios. I did want to mention at one point, which I didn't do, is that this is one of the climate toolbox tools here. All of the tools pretty much have the same layout. They have a tool, they have the location up here in the left, and then they have the different boxes for selecting things. But up in the right here, we actually have documentation. This is where you find information on the data source, like for instance, the MACA data, like what you can find a citation, you can find resolution information, maybe also links to the data pages or the original pages. You can get information on the variables where if you click on this, you get a definition, just in case you're not familiar with some of these definitions. There's also some information on the tool here. And there's a site tool. This is again for citing it, so a reference. And then you can also take a tour. So this might be one of the first things that you do is to go through a tour of a tool. And all of the tools basically have this, the documentation and the tours and this basic layout. Yeah. So I think that's where I could end it. MTS, is there anything that I've forgotten? Yeah.
Yeah,
Yeah, there are
sounds
other.
great, Catherine.
Okay, perfect. That's great.
If you want to complete that sentence, please go ahead.
Yeah, so I guess I was just, the only other thing is that you could also, once you identify these models and you look at like projections of different metrics, you can also explore a little bit more of the specific models by going into some other of the future tools. So like for instance, in the future climate mapper, you can look at the future projections and actually find the model that you were looking at, and actually see what its raw projections are around your area. So you can explore those models that you get from the scenario planning and in depth across all the different variables. And then there are other tools as well to explore the projections. Yeah. Okay.
Thanks, Catherine. That was great. So, there are a lot of questions coming in, so maybe you can provide some quick answers to some of these. So the first set of questions were around the historical simulation and observed data. So kind of you can talk about the difference between the observed gridded data and the MACA historical simulation, the differences, and also the question around the range of 1950 to 2005, why you didn't have data prior to 1950 and such. So thoughts there.
Yeah. Okay. So I will answer the second one first. So when we chose for the MACA data, like we wanted a consistent set across all of the, across all the different models and the scenarios. And not all models had the different variables that we were looking for. We were looking for some extra variables besides temperature and precipitation, like wind speed and radiation and humidity. Specific humidity and relative humidity. Not all models had that, and that basically drove our selection for which models to include with the MACA data. Also, some of the models did not have data before 1950. So some of them had data from 1800 or 1850, to 2100, even 2300, some of the models. So we chose to start at 1950 because of the availability that we saw from the models. Also, 1950 is somewhat of a good spot to choose just because of the start of the good data taking with the satellite era. Yeah, and then the first question was the difference between the GridMet data, the observational data, and then which is actual observed data, but it's been run through a model. So GridMet uses PRISM, Daily PRISM, and then also NLDAS2, which is a reanalysis satellite product. And so those are really like observations of what really happened in those years. And the GCMs, the global climate models, also run a historical 1950 to 2005 for the CMEP5. And they run those historical runs because they want, well, because it gives insight into the model actually, and it gives insight into what biases there are in the models. And so those biases can be used when you compare with the training data like GridNet to actually remove biases from the future data and also from the historical data. So you can correct it if you have that historical data. In our downscaling process, we do map the historical global climate model data statistics to the GridNet data, but we do that on a monthly basis. And so when we do it on a monthly basis, you can still get variations by model for something that's not monthly. So for example, here we've got winter precipitation. And so you see here a spread over the historical models, the historical scenarios for the different models. They're giving different answers, even for the winter precipitation. You can see there's a spread here from 8.6 inches to even 7.9, which is actually kind of small. It's only like 0.7 inches between the top and the bottom. And they should be centered around like a value from GridNet. But there is some variation in the historical scenarios over the different models, but they have been also bias corrected to GridNet. So they should be close to GridNet statistics when you consider something other than like monthly values of precipitation or monthly values of temperature.
Yeah, and question. Yeah, great. And I'll quickly add a couple of things. Is that the means of these historical simulation by these models should match GridNet, but not the variability, historical variability. So a 2012 year in these models will not actually match a 2012 year in the observed because model has their own variability. So keep that in mind. The other piece that's important that people who do analysis recommend is work in the model space. If you're looking at changes in future to develop your model on historical simulation data, and then and kind of use the consistent data. So work in the MACA space rather than use GridNet for historical and MACA for future changes.
Right. So for an example, if you're going to use the IPSL, the Murok ESM, and you want to look at projected changes, you look at the value for the future, and then you go and find the Murok ESM in here in the historical and use that for the historical and then compute a change between the future and the historical value for that model. Yeah.
This might be quick for you to answer. Like when you showed the polygons map, the question is, are all cells that are covered by the polygon, are they used for analysis? So even if the polygon's passing through a small part of the grid cell, will that be considered in the analysis?
Yeah,
does it have to include the center?
Right, right. So what happens there is that when I, for example, when I'm drawing a grid cell, this one doesn't have, that's interesting. It doesn't have the grid cell centers on it. Oh, shoot. Maybe I should go to the other tool real quick. That's interesting. That doesn't have that. Okay. Okay. Oh, this doesn't have it either. I don't know why that's not happening. So when I draw a polygon here, and it's hard to do this without the grid cell centers, unfortunately. It's going to do an area average over all the grid cells that over all the grid cells where the grid cell centers are inside the polygon. So for example, the grid cell center would be like right there. And so this grid cell would be used in the area averaging. Whereas this one, the grid cell center might actually be a little bit outside of this polygon here. So this grid cell might not be used. So that's why it's kind of important to see where those grid cell centers are or not, because you can spend a lot of time refining your polygon, but if it doesn't include more grid cells or less grid cells, it's not going to change the answer.
Yeah, and that you need to worry about. Need to consider that climate change is happening over larger spatial scales, and not worry too much about whether a grid cell is getting included or not. So I mean, yeah, don't get heartburn around those things a lot. The next question is around, does future climate scenarios tool only produce output for a point location? And yeah, that's not true. You can it does for all different spatial region selection. So
that's right. Yeah. So point locations, but then also these area averages, and you can customize it as well. Yep.
The next question is, are scenarios 1, scenarios 2, scenarios 3 plausible scenarios? I think the answer is yes. Can I change to fit the watershed I'm working with? And I guess the answer is yes, they're right, Catherine.
Yeah, you can
So
definitely. You get to tailor this completely how you want it, and you can also like name this whatever you want it to, right? So it can be the cool model, right? Yeah, so you can definitely change, the RCPs and the model that you use to get the report. Yep. And we have
And
a 5 here. Go ahead.
John,
Well, I think one approach to that watershed question would be just to upload your GIS shapefile of the watersheds themselves and generate the tables for your scenarios based
Yeah.
on that shapefile.
That's right. And we showed that. That's an excellent point.
um,
You can select just the polygon in your watershed that you are interested in getting averages from.
the next question is, looks like you have a lot of options for select climate variables. Is it possible to add new derived metrics? If so, what's the process around that?
Yeah, that's a good question. It's kind of where I met MTS, I think, in the first time, is MTS suggested some different metrics to the toolbox, just kind of like through email, just the contact, right? So you can under the documentation, like you can find my email. And there's also a contact for the climate toolbox as well. So that's under contact and ask questions, report issues. So you can get in contact with me, and if there's a metric that is pretty easy for us to calculate and it is a useful decision-making metric, suggest it and we can see if we can put it in. It's definitely doable. And yeah, we don't necessarily have a formal process for adding more. It's very informal.
Yeah, and I would add, this is John, that's kind of been the iterative process we've been going through with the service has been going through with Catherine and MTS for several years with the climate toolboxes. There'll be a metric that isn't available that we need for a certain species, and we make that suggestion to Catherine and MTS, and they're always really open to adding those if they can. So I'd encourage that if there's something that's not there to mention that to Catherine and MTS.
Yeah. And some are easier to add than others, of course, but if it's an easy lift, I definitely like it when, the stuff that we are producing here is used. So if it's something that you would use, I'd be more amenable to adding it, actually.
We will take one more question before we move into the informal session. It's from Megan Oldfather. It looks like a selection of climate models for each potential scenarios. Man will do these models update automatically if different location is chosen. And Megan, feel free to jump in and clarify the question, but
yes,
yes, go ahead.
So sorry if that wasn't clear. I just kind of missed with the climate scenarios tool. I was really excited about it, so I just wanted to fully understand it. That for scenario 1, the current model that's in there, that's just like an example model. It's
just an example. Yep.
Okay, it's not relevant. It's not okay.
No, everything here is filled out, and it only gets put in the table if you check this box. So for example, these are filled out down here just as examples, but if you don't select the box, it's not going to go in the table. So that's just an example, and then I can choose it and I can change it. And then I can write this too as the cool model. And if I've selected it, then when I make the report, it's going to say the cool models in there. And this is the cool model. Yep. And it only, yeah, that's right.
Thank you so much.
And maybe one more question we can get in is around climate analogs. Is there a way to expand beyond the Park Service localities?
Oh, so I think you're asking about the climate analogs tool, which we did not mention in this, but it is also an interesting tool. It's a tool for another webinar. And it does have like all the different models. So you can look at analogs for the different models. Like once you've identified them for your scenario planning, you can look at analogs. And so here for the analogs, you choose a location. So I'm going to choose John Day fossil beds. And I basically get the best climate analogs for, initially this is historical. So these are current day climate analogs, and these are the dark blues. So for John Day, if I'm looking at moderate heat stress, the best analogs for John Day are like these dark blue here. So the question was, can we expand beyond national parks? It's a lot of data. And so likely this is not going to get expanded beyond national parks because like it's just a lot of data to even run the national parks. For every location here, we have actually
Catherine, maybe we can take it to the informal session.
yeah,
If Jeff wants to join that.
that's a good point.
But really, once again, thank you all for joining the presentation today. We'll end the formal part now, and feel free to join for the informal session, which will hang around for 15-20 minutes.
Okay.
And I want to thank again our speakers for today, Catherine and John, and we'll hope to see you next month. And please have a good one.
You all.